Hello everyone, I'm Kaichen Yang from Peking University. I'm going to introduce ChameleMon shifting measurement attention as network state changes. Flow level measurement is critical to successful network operations, and there are mainly two kinds of flow level measurement tasks. The first kind is packet accumulation tasks that focus on flow sizes at certain network nodes, including flow size estimation, heavy hitter detection, entropy estimation, and so on. The second kind is packet loss tasks that focus on changes of flow sizes between network nodes, among which the most representative one is packet loss detection. However, the two kinds of tasks are seldom considered and supported simultaneously in one solution. One reason behind it is that the two kinds of tasks require very different flow level statistics. A practical measurement system should first meet the versatility requirement that the system should support both kinds of tasks because they are often required at the same time in real-world scenarios. The system should also meet the efficiency requirement. Given the limited resources in programmable switches, the system should achieve high accuracy with sublinear space complexity. Further, given the variable network state, the system should meet the attention requirement that the system should pay different attention to different kinds of tasks for different network states. When network state is healthy and there are only few packet losses in the network, the system should pay more attention, for instance, allocate more memory to packet accumulation tasks. When network state is ill and there are lots of packet losses in the network, the system should pay more attention to packet loss tasks to help diagnose network faults. Existing solutions fail to achieve both versatility and efficiency simultaneously. Some solutions support only packet accumulation tasks or loss tasks, and thus lose versatility. Typical solutions include elastic sketch, ChameleMon, loss radar, and NetSeer. Other solutions support both kinds of tasks with linear space complexity and thus lose efficiency. Typical solutions include flow radar and OmniMon. These solutions record exact IDs and sizes of all flows, incurring unacceptable overhead. A straightforward solution to achieve both versatility and efficiency is to combine solutions for accumulation tasks and for loss tasks. However, the straightforward solution cannot meet the attention requirement. The reason behind is that the data structures and operations of solutions for the two kinds of tasks usually differ significantly, which prohibits flexible memory reallocation between accumulation tasks and loss tasks at the runtime. We designed ChameleMon, the first system meeting versatility, efficiency, and attention requirements simultaneously. We name our system ChameleMon because its key design is to shift measurement attention as network state changes, which is just like the process of chameleons changing their skin coloration. The methodology to realize the key design is to propose a homogeneous data structure while achieving versatility and efficiency simultaneously. With the proposed data structure, we can divide it into multiple parts to support different kinds of measurement tasks and flexibly move the division point at runtime to achieve memory reallocation. As shown in the slides, when network state becomes ill, we can move the division point to the right to allocate more and more memory for lost tasks. To this end, ChameleMon incorporates a key technique leveraging Fermat's Little theorem to propose a flexible data structure, namely Fermat's sketch. Fermat's Little theorem states that if p is a prime, then for any integer a that is indivisible by p, we have that a to the p-1 power modulo p equals to 1. The data structure of Fermat sketch consists of d bucket arrays. Each bucket array contains a count field, which records the number of packets hashed into it. Each bucket also contains an ID sum field, which records the sum of flow IDs hashed into it. Fermat sketch also maintains a large prime P, which is used to compress the ID sum field into a prime field ZP. To insert or encode a packet of flow F, we locate a bucket in each bucket array with hash functions. For the count field of each located bucket, we increment it by 1. For the ID sum field of each located bucket, we increment it by F and then modulate it by P. The deletion operation is similar to insertion and that all increments are replaced by decrements. To decode Fermat sketch to retrieve all inserted flows with their sizes, we need to first find pure buckets, and we call this step pure bucket verification. A pure bucket is a bucket which records only a single flow. Suppose a bucket Bij is a pure bucket recording flow F. We can easily obtain its flow ID, denote the count field and ID sum field of bucket Bij by count and ID sum respectively. It should satisfy the ID sum equals to F multiplies count modulo P. With Fermat's Little theorem, we have come to the p-1 power modulo P equals to 1. Then we have that F equals to ID sum multiplies count to the p-2 power modulo P. With calculated flow ID, we can then execute rehash verification to check whether the bucket Bij is a real pure bucket. After finding a pure bucket BIG, we then can extract the recorded flow with its flow size, and we call this step single flow extraction. Besides, Firma Sketch also support addition and subtraction operations. For packet loss detection, we can deploy Firma Sketches on edge switches to encode all the traffic entering and exiting the networks. Then we can get Firma Sketch encoding all the victim flows through additions and subtraction, and we can finally decode that sketch to detect packet losses. For heavy hitter detection, we can deploy Firma Sketches on edge switches to encode heavy hitter candidates at edge switches, and then decode those sketches to detect heavy hitters. Every measurement window, ChameleMon first captures flow-level statistics by implementing Firma Sketches on edge switches, covering all the traffic entering and exiting the network. Second, ChameleMon collects sketches from edge switches. Third, ChameleMon performs network-wide analysis to obtain real-time network state with the collected sketches. Fourth, ChameleMon shifts measurement attention according to real-time network state by reconfiguring the switch data plane. We then introduce the design philosophy of data plane of ChameleMon. When the network state is healthy, that there is enough memory to record all victim flows. At this time, ChameleMon should record as many heavy hitter candidates as possible for accumulation tasks. When network state is ill, that there is not enough memory to record all victim flows. At this time, ChameleMon should focus on recording heavy losses, which refer to victim flows suffering from severe packet losses. Meanwhile, ChameleMon should also sample some light losses, which refer to victim flows suffering from few packet losses, so as to maintain an overview of all victim flows. Based on the insight that larger flows can lose more packets and thus have a higher probability to become heavy losses, ChameleMon uses flow size to classify heavy hitter, heavy loss, and light loss candidates. The packet is inserted into a large Firma sketch, which consists of 3 parts working as 3 flow encoders. It is inserted to a corresponding encoder according to its classification result. When a packet leaves the network, it is also inserted to a large Firma sketch. Because heavy hitter candidates are already recorded upstream, the Firma sketch only consists of 2 encoders, and all heavy hitter candidates are inserted into heavy loss encoder downstream. In this way, ChameleMon can support 6 packet accumulation tasks and packet loss detection. Then we should use the design of control plane of ChameleMon. ChameleMon considers the network state as healthy when it can record all victim flows. At this time, there's no need to sample live losses. The threshold for heavy losses is set to 0, and ChameleMon allocates no memory for light loss encoder. On the healthy network state, ChameleMon shifts measurement attention to maximize measurement accuracy through 2 dimensions. First, ChameleMon allocates appropriate memory for heavy loss encoder to record all victim flows, which is achieved through flexibly moving division point between heavy hitter and heavy loss encoders. Second, ChameleMon sets heavy hitter threshold to appropriate value to record as many heavy hitter candidates as possible. ChameleMon considers the network state as ill when it cannot record all victim flows. At this time, ChameleMon should sample light losses. With the threshold for heavy losses setting to larger than 0, the memory allocation between heavy hitter, heavy loss, and light loss encoders should be fixed, as no more memory can be allocated to record victim flows. Under U network state, ChameleMon shifts measurement attention to maximize measurement accuracy through setting heavy hitter threshold, heavy loss threshold, and light loss sample rate to appropriate value so as to record as many victim flows and heavy hitter as possible. Finally, we show the experimental results of ChameleMon. For packet loss detection, we find Firma sketch has best memory efficiency with memory overhead proportional to the number of victim flows. For 6 packet accumulation tasks, Firma sketch achieves at least comparable accuracy with the state-of-the-art solutions. To evaluate how can ChameleMon shift measurement attention, we have fully implemented a ChameleMon prototype on a testbed with 10 Tofino switches and 8 servers. We manually change network state, including the number of total flows and the ratio of victim flows. Results show that ChameleMon can successfully shift measurement attention while maintaining high memory utilization. In conclusion, ChameleMon is the first system meets versatility, efficiency, and attention requirement at the same time. ChameleMon is also the first system supports packet loss detection with memory overhead proportional to the number of victim flows. We have fully implemented ChameleMon on our testbed, and extensive experimental results verify its effectiveness. That's all. Thanks for your listening.